Okay, so we will start the class by question first. Do you have any questions from last time or your assignment? Hmm?
No, Professor.
You say something?
Yes, Prof.
Yes. You have any question, Kadim?
Yes, the assignment questions, I attempted to use duality approach, but
Mm-hmm.
it seems the answer I got is different from when you use two faces.
I cannot get your question. Was it?
No, the question is when you use a two-face
Dual.
method,
Yeah, dual simplex. Mm-hmm.
yes, and dual simplex, the answer seems to be different.
Really? Can you show me your your problem?
Uh,
You try both method, right?
no, I solved with just duality method, but I
Mm-hmm.
stopped the algorithm when all my B's are non-negative.
Mm-hmm.
But if you use the other approach, you can still proceed to the. So I don't know why. Maybe I will look at it again.
You look at my what's it solution?
Yes, I saw the solution. The solution is not duality method, so maybe that's why there is difference.
Yeah, I solved the problem using the two phase. Mm-hmm.
I will check it again.
Okay. So we move to our today lecture. Well, previously we deal with linear programming, right? So our limitation is on the what's it objective function and also constraint. All the constraint and objective function must be linear function. Okay, and now we move to nonlinear programming. Well, for nonlinear programming, actually it's a kind of a very broad category because, well, your objective function can be nonlinear, your constraint can be nonlinear too. Well, in some case, well, as I mentioned to you, it's quite broad because in some case, if our constraints are linear function, only the objective functions it's nonlinear. Well, we have special class of problem, or our objective function is quadratic, and our constraint form a convex region. Well, of course, we have a special case. So, but well, in as a broad, I mean, well, the idea that can solve any nonlinear programming. Well, the basic idea of the most of the numerical method, I mean, the algorithm of the optimization for the problem in this class, I mean, nonlinear programming. While we produce a sequence of a improved approximation to the optimum according to the following scheme. We start from the initial trial point, let's say x1. Well, we choose x1 starting from any point because it's trial point. And then we move to the next point by using direction and also step length. We have two keywords here. We have suitable direction and step length. So the problem is, well, how to select or design a suitable direction, okay, as that points in the general direction of the optimum. Okay, we start from x1. How do we know that we which direction that will go down? Okay, imagine that you are on the top of the hill and you want to go down. Of course, you need direction, right? And those directions must point to the lower region. Okay, because you are top on the hill and you are going to minimize. So, well, the first question is on direction. You need a direction. Maybe direction is not unique direction. You can use any direction that points out, right? Of course, for the steepest descent or the direction which is has the maximum slope, it's we call it steepest descent, will lead to the shortest path. But you don't have to follow that direction. You can go down by any direction as long as that direction pointing down. Okay, so for the second step, we find a suitable direction that points down, right? Points to the optimum. Okay. In case of maximum, of course, it's point up to the maximum point. And the next step is find an appropriate step length. We call it lambda I star for the movement along the direction. Okay, you specify the direction previously, and then you choose the step length. Well, for example, if you are top of hill, right? You select the direction and then you decide how long do you want to step along that direction. Okay, of course you go further down, right? In case of minimum, you go further down for a specific length, and then you design again what to do. Okay, so once we have direction, we have a step length, then we can find a new point, right? So a new approximation is xi plus 1. The next step is xi, okay, a trial point plus lambda I si. Okay, si is our direction, and lambda I star is our step length. Okay, so once we obtain xi plus 1, our next step, we have to test whether the obtained point is optimum or not. If xi plus 1 is optimum, then we stop the procedure. Otherwise, we set a new iteration and repeat step 2. Repeat step 2 means, at that point, if it's not optimum point, then we determine again the suitable direction, and we find again a step length, okay, appropriate step length. So you see that it's very simple. We transform any dimension to a one-dimension problem, right? Because we go along the direction, then that means, for a higher dimension, we transform our optimization problem into a single or one-dimension problem. Okay, along direction S. I mean, along the direction. For example, if our trial point, we start from here, x1, okay, and we select s1, so we have to go along s1, go along this direction, and we have to determine, by along this line, I mean this direction, how long the step length is. So we have to determine the direction and then the step length, and we obtain new point, right? And from the new point, we test against the optimality condition. For example, what we learned previously, the optimal condition of a Lagrange or KKT, right? You can use those KKT as the optimal condition to test whether the point is optimal or not. All right, so we obtain x2. And then from x2, we determine again the direction. Let's say, well, if our algorithm obtain this x2 direction, we go along this way again, and you have to decide how long we should go along this direction. So we move from x2 for lambda 2 star, and we reach x3, okay, which is our adjacent point. Again, we test x3 if it is optimum point or not. Okay, if not, in this case, like in this case, so we determine direction again. We obtain the direction S3, which is, yeah, pointing toward the optimum point. And then along this direction, we determine again the step length, and we move to x4. Okay, and we repeat it from x4. We determine direction, and then, well, we determine the step length. Okay, we move further down. Okay, this is the idea of nonlinear programming. So you see that the efficiency of the algorithm depends on the efficiency with which the quantities of lambda I star and Si are determined, right? So how fast we can reach the optimum point depends on the direction we determine at each step, and also depends on the step length we determine at each step. Okay, so in order to improve the performance, well, we have to study more on the method to identify the direction, and also the method to identify the step length. The method of finding the step length lambda I star are considered here. Okay, we consider the method to finding a step length first. Okay, for the direction we will deal with later. Okay, we assume that we have direction already. So, well, if we have the direction already, as I mentioned to you previously, that we transform our objective function from higher dimension to one dimension problem. So if fx is the objective function to be minimized, the problem of determining lambda I star reduced to finding the value of lambda I star that minimize the fx, right? Because we transform our fx, which is a function of Decision variable in case we have multiple, many decision variables, then we transform our fx to one dimension. One dimension means, well, the objective function is transformed to be a function of step length, lambda I. Okay, because lambda I is a scalar, right? Okay, only one variable. Now we have, because I assume that we have direction already. Once we substitute the direction to the original objective function, f becomes our objective function becomes a function of one variable, which is step length only. And the method of finding the step lengths are called one-dimensional minimization method in case of minimization problem. But of course, in case of maximization, you can change to minimization, or you call it, one-dimensional maximization method. Yeah. So for one-dimensional minimization method, for numerical method, we can separate into two categories. It's it's elimination method and interpolation method. Okay, and for elimination method, well, there are many algorithms. For example, heuristic search, exhaustive search, dichotomous search, Fibonacci method, or golden section method. I will show you some of these methods. Okay, elimination method. Also, we have interpolation method. Okay, and interpolation method, there are two categories. The first category is a method which require derivative, okay, or well, some method doesn't require the derivative, okay. For the method that requires the derivative, for example, the Newton method or cosine Newton or secant, these methods well make use of the derivative. Okay, so while we will start from elimination method first. Okay, before we go further, let me well introduce you the concept of unimodal function first, because we need this concept in order to establish our algorithm. So let's say a function fx is unimodal. Okay, function fx is unimodal if the first case x1 less than x2 and less than x star, which is x star means well our optimum point, implies that fx2 is less than fx1, right? And well, we assume that fx is unimodal. Okay, if x1 is less than x2 and also less than x star, it implies that well, if x2 is less than fx1. Okay, and the second case is if x2 is greater than x1 but less than x star, it implies that if x1 is less than fx2, okay, where x star is the minimum point. Okay, for example, we have a and b here. If the function f is unimodal, and you see that well, this function, well, the value of the function, I mean fa, is greater than xb. No, fb, fxb, fxa is greater than fxb. And you see that if the function is unimodal, so it should be wow, looks like this because it's unimodal. All right. So wow, and you see that our concept can be applied to any type of function. Okay, for example, wow, discontinuous function or the function where we have some points in between has no derivative. Also, well, it's applicable for this kind of function too. So, as I mentioned to you, a unimodal function can be a non-differentiable or even discontinuous function. Okay, and if a function is known to be unimodal in a given range, for example, well, let's say in 0 to 1 or a to b, whatever, in a given range, we know that it is unimodal. The interval in which the minimum lies can be narrowed down, right, by providing the function value. Well, and we can eliminate some. For example, if we know from in the range of 0 to 1, we know that our function is unique modal function, and we test against the points x1 and x2. We obtain f1 and f2 here. We can eliminate some region, some area of the original area, right? Now we have 3 areas. Yeah, the first area is from 0 to x1, and the second area is x2 to x1 to x2, and the third area is x2 to 1, right? And we know that our function is unimodal function. We can eliminate one area. What do you think? Which area we can eliminate? We can guarantee that our minimum point will not lie on that section. Kadim, what do you think? Which area we can eliminate?
Sorry, bro.
Yeah, from the first, from A picture, figure A.
Okay.
We know that our function is unimodal function. Okay, unique modal function in a range from 0 to 1. And we have this information that x1 at x1, x2, x1 of course is less than x2, and f1 is also less than f2. We have three regions, right? We have region from 0 to x1, x1 to x2, and x2 to 1. Well, from the concept of unimodal function, we can guarantee that our minimum point cannot lie on one section. Any section we can eliminate. Any section we can guarantee that our minimum point will not lie in that section.
Okay.
So from zero to x1.
You say from 0 to x1?
Yes, sir.
How about from S2 to 1?
Yeah, from x2 to 1. Okay, all right. I will explain why we can say that we can guarantee that in this region the minimum point cannot lie in this region. Because, well, you see that this is unimodal, right? Unimodal means, well, you have only one loop in here. So you see that this region, F1 is less than F2, right? So it's impossible that we have another, a reflex here, right? The function cannot go down here because, well, it's already go down here. Okay, so we can eliminate x2 to 1, this region. Okay, from x2 to 1, we can say that our minimum point cannot lie in this section anymore. Yeah. Can we say that the minimum point lie in this region or this region? The answer is no. You cannot say that your minimum point lies in this region or this region. Yeah, it can be any, I mean either here or here. Because of what? Because, well, you see that unimodal, you can draw the function like this, down here and up again, right? Or go down here and up here. So, well, let me draw in the function for you. You can see my screen, right? Okay, from this region, this region from 0 to 1, let's say. And we have x1, x2 here. Right, we have these two. And you see that, well, for unimodal, it can be like this. Okay, it's still unimodal, right? Or it can be like this. Or it can be like this. Okay? All of them are unimodal function, right? So what we can do is just, well, we can eliminate this region. Because it's impossible that our minimum point lies around this region, right? Because of what? It cannot, well, like this, right? Okay. You get my point? Do you understand what I explained? Asan,
Sir, kindly repeat this point again.
pardon? Well,
Sir, kindly,
your voice is not clear.
sir, kindly repeat this point again.
All right, so yeah, okay. Wow, we have information about this, right? This is F1. F1, this is F2, right? We know that, you know, the concept of unimodal. For unimodal, it should be like this, yeah. So, but we don't know the width or the, yeah, the width of this curve, but it's unimodal. You know, unimodal should be like this. So you see that if we have information about F1, F2, F1 is greater than, no, F2 is greater than F1. So you see that our function can be like this, okay? In this region, it's unimodal, right? Or it can be like this, okay? It's still unimodal, but it cannot be like this because it will not unimodal anymore. All right, so you cannot say that, well, our minimum point lies between x1 x2 to 1 in this region. Is impossible. This region is impossible because we have this point which is lower than this point. So we know that the direction of the, well, the minimum point should be on this side. We go down, yeah, but it can be here or here. It depends. Okay, so we cannot eliminate 0 to x1 or x1 to x2. Yeah, but from x2 to 1, you can delete it. You can eliminate this region because our minimum point cannot lie in this region.
Yes, sir. I got you.
Okay, what about figure B? For figure B, well, Ahmad, can you tell me which part we can eliminate from our, yeah, possible region? I mean, the region that contains the minimum point.
Ajahn, in my observation, it should be 0 to x1.
Yeah, yes, you're right. From 0 to x1, wow, the minimum point cannot lie in that region. Okay. What about C, figure C? Sakum, what about figure C?
I think from x2 to 1.
X2 to 1?
Yeah.
Okay. This is special case. X2 to 1 is, yeah, it's correct, but you can also eliminate 0 to x1 too, because it's the same, right? So because F1 and F2 are identical. Okay. So the minimum point should be in between x1 and x2. So you can eliminate both regions. Okay, so consider the normalized interval 0 to 1 and two functions evaluation, which are f1 and f2. F1 and f2, like that. So if the outcome is that f1 is less than f2, f1 is less than f2, f1 is less than f2, the minimizing x cannot lie to the right of x2, right? Here, this section, the minimum point cannot lie here. Thus, the part of the interval x2 to 1 can be discarded, and a new smaller interval of the uncertainty 0 to x2, okay? 0 to x2 contains our minimum point. And if f1 is greater than f2, f1 is greater than f2, then the interval 0 to x1, this interval, can be discarded to obtain a new smaller interval of uncertainty x1 to 1, right? And if f1 equal to f2, this interval 0 to x1 and x2 to 1 can both be discarded to obtain the new interval of uncertainty as x1 to x2. Okay, such with a fixed step size. The next one. The most elementary approach is to use a fixed step size and move from initial guess point in a favorable direction. Okay, we call it heuristic search. So we start from initial guess of point 1 and find the f1 and assuming the step size f and then find x2. Okay, we have x2, which is x1 plus s1, and then we find f2. Okay, so for heuristic search like this, the algorithm can be, well, we start from x1 and we find f1, and we find some step size s, and then, well, x2 is x1 plus s, and then we find f2. Now we have f1, f2, right? So we test f1 and f2, right? Using the same technique here, because we assume that our, well, we have to guarantee first that our function is unimodal. And with that information, we reach 2 points, x1, x2, and we evaluate f1 and f2, then we can eliminate some area, okay? And we give a smaller area, right? Smaller area of uncertainty. And then we repeat again, okay? Then, wow, with several iterations, we can narrow down the uncertainty area, the uncertain area. Okay, so this is the algorithm of heuristic search, which is a kind of the elimination method. So any questions? You have any question?
No, sir.
Okay. All right, so for example, let's say we have this function. We want to minimize fx, which is lambda power by 5, okay? Minus 5 lambda power by 3 minus 20 lambda plus 5. By using heuristic search with a fixed step size of 0.1 starting from lambda, it's 0. Okay, so you can use Excel, right? Yeah, starting from 0. Okay, and the step size is 0.1. Okay. With x, we evaluate fx. Okay, we can see the, wow, this value, and you can capture the, what's it, the trend of the function, the, yeah, how the function looks like, yeah, and eliminate some part. Okay, so well, also the search with the fixed step size appear to be very simple, and but the limitation is of this heuristic search is it's quite slow, okay, and involve a large amount of computational work. So we need some improvement, okay, and the idea is search with accelerated step size. Okay, it's a method consisting of a doubling step size as long as the move result in an improvement of the objective function. Okay, and also one possibility to reduce the step length after bracketing the optimum in the xi minus 1 to xi by starting either from xi minus 1 or xi. Okay, and the basic procedure can be applied with a reduced step size. Okay, and we repeat that. Or we can use exhaustive search. So for the exhaustive search, well, it's the method involves evaluation of the objective function at a predetermined number of equally spaced points in the interval. For example, we have a region between xs to xf, and reducing the interval of uncertainty using the assumption of unimodality. Okay, we use the concept of unimodal function. If the function is evaluated at n equally space, okay, we have what's it, xs to xf, right? So the space between is what's it, the length, it's actually the xf minus xs, okay, and we equally distributed to n equally spaced point. So we have to divide it by n minus by n. Okay, so you see that with this one, for example, we have xs to xf and we equally space them. Okay, you can choose n, I mean the number of equally spaced. Okay, and you don't know this function. All you have to do is just you equally divide it xs xf to n space. Okay, and then here we have a 9, right? 9 space, and then while we evaluate our objective function at each point, at each point, so you see that we can remove some of them. I mean, at each step we can remove some part out. Okay, so from this one, you see that we divided by 8, right? By 9, right? Sorry, 9. We have 9 space here, and you don't know this function. So, but we know that from this direction, the objective function decreasing, right? Decreasing. And from this direction from right to the left, objective function also decreasing. And you see that the remaining uncertain area is here from x5 to x7, just that. From x5 to x7, only this region. You can eliminate this part out and this part out. Even you don't know exactly the feature. You don't know exactly how the function looks like, but you can guarantee that your minimum point can lie in this region or in this region, just that. It cannot lie on this region. It cannot lie on this region. Okay, only this part. Okay, so we will deal with exhaustive search in the interval of 0 to 5 in this problem. Again, we deal with the same problem again. Oop. We choose n to be 10. And of course, the interval, well, we deal with interval from 0 to 5. Okay, 0 to 5. So the length of the interval is 5. And the n, we choose n to be 10. You can change it, okay? And you evaluate the, well, you construct the x first, I mean, x1 to xn, okay? In the, well, area starting from 0 to 5, 0 to 5, and then you equally divide it, and, well, you evaluate the fx, this fx, okay? And look for the reflection of the objective function. You see that from this direction, it's going down, right? It's decreasing, and from this direction going up, it's decreasing again. And you, well, our uncertain area is just from 1.5 to 2.5, only that. The rest we can eliminate. Okay, and then you see that now the uncertain area shrinking to 1.5 to 2.5. So we repeat the algorithm again, but the interval now starting from 1.5 to 2.5. Okay, and the length here is 1, and if we choose the same number of n, the same n, which is 10, okay, so you equally space from 1.5 to 2.5, and then evaluate fx inside that. Okay, and you see that our uncertain region now starting from 1.9 to 2.1, this region. Okay, so you see that we can narrow down our uncertain region. We repeat it again. Now, well, our area of concern is just only from 1.9 to 2.1. So for the next step, we start from 1.9 to 2.1, and we divide it using 10. Again, we can narrow down the uncertain area. So we can guarantee that the minimum point must lie between 1.98 to 2.02. Okay, this region. Okay, any questions?
Yes, John.
Yes. What's your question?
Yeah. On what basis we select the range between 1.5 to 2.5 in first case?
Mm-hmm.
We could
1.5 to 2.5, yeah.
Yeah, we could have gone for 2 to 3. It's
2 to
uncertain.
3.
Yeah.
Okay, so you see that it's from, it cannot be on this region. I mean, from you plot it down, you can see that because it's going up again, right? So how to say, you see that, well, the minimum point we we obtain now, it's minus 43, right? Minus 14, and then going up, and this, and then going up. Okay, and you see that from what's it, from 4 to 3 is going up, and from 4 to 5 is going up again, increasing. I mean, this increasing and this increasing. So we have assumption that our function is unimodal. So if it's going up, increasing, it will be increasing. All right. Here also is increasing, it will be increasing. So minimum cannot be, yeah, beyond this point, because if minimum beyond this point, that means, well, the function is decreasing again. So it's not unimodal.
Yeah, okay.
Sorry, Professor.
Yes.
Yeah, can we just assume any function to be unimodal, or what information do we need to know if
Okay.
the assumption is correct?
Yeah. That is the very important question. We can use convex analysis. Okay. We should test for the convex function. If the function is convex, you know that it must be unimodal, right?
Yes, I think.
Just that. In this region, the function is convex. Well, you guarantee that we have it. It must be unimodal. Okay. Any more questions? Okay. If not, we move to the next one. The next algorithm we call dichotomous search. Well, previously we deal with exhaustive search, right? Of course, for exhaustive search, well, if you need a fewer iteration if you use higher number of n. But of course, while use higher number of n, you have to evaluate function more. I mean, yeah, the computational load, yeah, it's greater. Okay, so in the dichotomous search, we use different strategy. We use two experiments. Well, two experiments are placed as close as possible at the center of interval of uncertainty, based on relative value of the objective function at 2 points. For example, we start from, yeah, we have L0, which is the length, right? The interval of uncertainty, the starting interval of uncertainty. Then, well, we divide it. We determine the middle point, and then from the middle point, we move, yeah, to the right and to the left for a certain distance. For example, in this case, x1 is, yeah, L0 over 2, subtract by delta over 2, right? And next for x2, just we start from the same place, L0 over 2, but now we move to the right, yeah, by plus delta over 2. Okay, then the new interval of uncertainty is given by L0 over 2 plus delta over 2. Okay, and you see that the final interval of uncertainty after we conduct an experiment, yeah, can be given by this expression. If you repeat it for n times, yeah, Ln becomes, Ln is the interval of the uncertainty, becomes L0 over 2 power by n over 2 plus delta times with 1 minus 1 over 2 power by n over 2. You see that what is it? Ln decrease faster than the previous method. So I show you again the dichotomous search, how it works. Okay, in this case, we deal with the same objective function, and we use dichotomous search in the interval from 0 to 5 with delta. It's 0.1001. Okay. So we start from 0 to 5, right? And we use L0 is 5, of course, because it's subtraction of the 5 by 0. So we choose delta to be 0.001. Okay, this is our parameter. You can change this parameter. Yeah, and from 0 to 5, the middle point is 2.5. Okay, and then we move back delta over 2. We move forward delta over 2. Okay, and we determine fx. Okay, and we eliminate some part out. Okay, So you see that, well, from the first iteration, we can eliminate, yeah, almost half of the area. So our interval now becomes 0 to 2.5. Yeah. Okay. And we do it again. The middle point from 0 to 2.5 is 1.25. Okay. And we move to the left. Yeah. Just delta over 2. And we move to the right, delta over 2. Okay. Then look at this value, and then we eliminate some part. We can eliminate, yeah, from 0 to 1.24995 out. So our interval, the area of concern is now becomes 1.25 to 2.5. Okay, we repeat it again. Okay, we repeat the same procedure. Okay, we can narrow down the interval of uncertainty. Finally, we know that, well, at this iteration, our interval is just, well, 1.9531125 to 2.031225. Okay. So then we move to the next method. We call it interval halving method. In the interval halving method, well, at each iteration, exactly 1/2 of the current interval of uncertainty is deleted. Okay. Each iteration, we eliminate 1/2 of the interval. Okay. And it requires 3 experiments in the first stage and 2 experiments in each subsequent stage. Okay. The algorithm starts from, well, we have L0, which is interval from A to B. Okay. We divide this L0 into 4 equal parts. If we divide it into 4 equal parts, that means, well, we have to we have to evaluate 3 points. Okay, let's say x0, x1, x2. Okay, we divide this to 4, and then we got new x0, x1, x2. Okay, and then we evaluate x0, x1, x2. Okay, we obtain f1, f0, f2 of course. Okay, like this, we have A to B, right? We divide it into 4 areas. Yeah, 4 intervals. And then we obtain x0, x1, x2. And then we have to evaluate the function at x1, the function at x2, x0, and the function at x2. Okay, so we obtain f1, f0, f2. Okay, now we have 3 possible cases. If f2 is greater than f0, like this, f2 is greater than f0 and f1. Okay, so we can delete the interval from x0 to b. Okay, we eliminate half of the interval, original interval. Okay, the area of concern now from A to x0 only. Okay, because minimum point cannot lie in this region. Okay, and the next case is case B. If f2 is less than f0 and less than f1, okay, we can eliminate the interval from A to x0. Okay, we can guarantee that our minimum point cannot lie in this region. Okay, minimum point must lie in this region. Okay, from x0 to b. If f1 is greater than f0 and f2 is greater than 0, in this case, we can eliminate this region and this region. Okay. Our minimum point cannot lie in this region or this region, right? Minimum point must lie, yeah, in this region from x1 to x2. Okay, so you see that in any cases, we can eliminate half of the interval. Okay, that is the reason we call this method as interval halving method. Okay, and then we repeat again. We test whether the new interval of uncertainty satisfy the convergence criterion. If the region is small enough. Okay, then we can look at the example. For example, we deal with the same problem. We minimize fx, which is lambda power by 5 minus 5 lambda by power by 3 minus 20 lambda plus 5. And the interval, which the starting interval is from 0 to 5. Okay, and the length of the interval is now 5, right? We divide this interval into 4 intervals. So we need to evaluate 3 points. Okay. And from the first iteration, you see that while we can narrow down, we can eliminate the region from, starting from 2.5 to 5 out. Okay. So our area of concern, interval of concern, is just from 0 to 2.5, 0 to 2.5. Okay. The length, decreased 50% to 2.5. And from this region, again, we divide into 4. Okay. And you see that for the second iteration, we have to evaluate only 2 points, right? Because at 2.5, 1.25, we have already evaluated the function. Okay. Yeah. So we have to evaluate the function at this point. I mean 0.625 and 1.875. Okay, and we eliminate the 0 to 1.25 here. So our area of uncertainty, interval of uncertainty, becomes 1.25 to 2.5. Okay, we repeat again. Yeah, we do that for several iterations, and you see that the interval become very close now, very small now. Okay, if it is small enough and objective function doesn't change much, we can assume that this point, our minimum, lies between this point. Any questions? You have any questions? Oh, sorry. Sorry, I cannot hear you, Hassan. Your voice not clear. We cannot hear you. You can type in the chat box.
No, sir, I don't have any question.
Oh, okay, all right. Well, what about others? Do you have any questions on this?
Hello, Prof.
Yeah.
Yeah. Will the method to solve the problem be specified in the question, or we can just choose to apply any method if it is a unimodal function?
Oh, well, if it's not fixed, if the problem does not, ask you to use specific method, you can use any method, right?
Okay.
Okay, but of course, you see that
Then
yeah.
same will go for the linear programming. We can use any method, or will be specified.
Yes, you're right. As long as you can use that that technique, that method to solve the problem, it's okay. If it's not specified.
Okay.
Okay, let me summarize. For exhaustive search, you can expect that the ln, the interval after n iteration, the area, I mean the length, the interval becomes this expression 2 over n plus 1 L0 starting interval. And for dichotomous search, this is ln, and this is ln for halving, interval halving. Okay, you can see that after 5 iteration, n is 5, and you see how the interval of uncertainty change. Okay, this is after n. Okay, we have break for 10 minutes first, and then come back again, to continue for quadratic interpolation technique. Okay. Okay, so let us resume. Okay, let's continue. So the previously I told you about the elimination method, right? Well, where we start from the interval of uncertainty, okay, the area of concern first, and then we use the algorithm to eliminate some part out. During the iteration, the algorithm developed, and then the interval shrinking. Okay. And finally, we obtain a small enough, small enough of interval, and then we stop, right? The next method is a quadratic interpolation method. For interpolation, you see, interpolation is totally different from the idea of the elimination. For elimination, we have interval, right? And then we eliminate, some part out. But for interpolation method, because we have trial, or even not trial, we have information of the objective function, and then we predict the minimum point directly from that direction. In this case, for the quadratic interpolation method, we use quadratic function to approximate the objective function. No matter your objective function, of course, your objective function is now one dimension, right? It's a function of one single variable, which is step length. Okay. No matter the functions how it look like, but we approximate the function to be quadratic function. And from the quadratic function, you know that the quadratic function is in this form, right? H lambda is equals A plus B lambda plus C lambda square. Okay, this is a quadratic function. And you know that any quadratic function, the minimum point is at this. Yeah, we can obtain the minimum point directly. The minimum point is minus B over 2C, right? Where B, C are parameters from this function, okay? The point is we have to approximate the original of the objective function to the quadratic function first, and then we obtain this directly. Okay, so for the sufficient condition for the minimum point is lambda is that, yeah, you learn it from the classical method. Okay, the next thing is to evaluate A, B, C from this approximated function. You need 3 points at least. Okay, well, you can choose any points. For example, lambda A is FA, yeah, lambda B FB, and lambda C FC. Of course, you need well, you rest that triangle point lambda A, and then you evaluate it to obtain FA. You evaluate the function to obtain FB. You evaluate the function at C to obtain FC. Okay, and then from these 3 points, okay, we have 3 points, of course, and we have 3 parameters A, B, C, right? You can, well, determine the ABC, the parameter for the approximated function as ABC using the point you evaluate here. Okay, by using these formulas, you can obtain ABC, and then you know that minimum point must be at minus B over 2C. Here, this point. Lambda star is minus B over 2C, where C is greater than 0. Okay, so if we select lambda A to be 0, lambda B to be T, lambda C to be 2T, okay? At A point, yeah, it's FA. Okay, at B point, is it 4FB minus 3FA minus FC over 2T, and C can be, yeah, evaluated from this. And our lambda star is at this point, because lambda star is minus B over 2C, right? Minus B, minus of this, yeah, over 2 times of this function. So lambda star is here, right? And the condition is the C must be greater than 0, okay? Also, yeah, if C plus FA over 2 must be greater than FB. That is the quadratic interpolation method. Okay, the concept is the same, but we approximate the objective function as a quadratic function. Okay, and the next method is cubic interpolation method. For cubic interpolation method, you know, because we use cubic function instead of quadratic function, so the approximated function must be in the form of h lambda. It's A plus B lambda plus C lambda square plus D lambda, yeah, powered by 3, the cubic of lambda, right? Okay, and well, of course, because we have 4 parameters, we have A, B, C, D. That means, well, we need 3 functions, right? 3 information. But of course, we can use only 2 points, but we resort to the derivative. Okay, we use information of the function of objective function and also the derivative of our objective function as at A and B, okay? By using this information, I mean, if A, if B, if prime A, if prime B, we can obtain the parameter for the approximated function, estimated function, okay, in a cubic form. And the next method is Newton method. We learn about quadratic, we learn about the cubic, right? Both of them are interpolation method, but the next method is the Newton method. Consider the quadratic approximation of function f lambda. You see that at lambda, it's lambda I. Using Taylor series expansion, we can approximate f lambda as using Taylor series. Okay, at the fixed lambda I. We use the lambda I as our fixed point, and then we expand the function using Taylor series. Okay, so if lambda, it's f lambda I plus f prime lambda I times with lambda minus lambda I. Okay, this is a linear term, and the quadratic term is here. Okay, the quadratic term is 1/2 f double prime of lambda I at lambda I, of course, times with lambda minus lambda I square. Okay, so if we take a first order derivative of this function, we obtain this expression. F prime lambda becomes, well, f prime of lambda I, okay, and f double prime of lambda I times with lambda minus lambda I, and this term becomes 0. Okay, so well, we know that at the minimum point, f prime lambda must be 0. So this is, we fix this value to be 0. Let this f prime lambda be 0. So we can rearrange this expression in order to obtain the lambda I plus 1. Okay, so we can relate between lambda and lambda I. Okay, so lambda I plus 1, or the next point is lambda I subtract by the fraction of f prime lambda I over f double prime lambda I. Okay, so if the function being minimized, if lambda is not available in closed form, or it's difficult to differentiate, we can use a numerical derivative of f prime lambda, or second order numerical, yeah, of f prime double prime lambda. Okay, yeah, we can approximate f prime lambda and f double prime lambda by using this function. Okay, this expression. Okay, so let me conclude what you have learned today. You learned about the idea of nonlinear programming. Okay, for nonlinear programming, we have to find the direction. We starting from, yeah, let's say we start from the trial point, and then you need direction, right? And from the direction, well, we use the direction that S to transform the multi-dimensional or higher order problem into one variable. I mean, yeah, one-dimensional problem. Okay, that means, well, we obtain the objective function, which is a function of only single variable, and then that from that single variable, from that single variable, we have several methods, several algorithms to find the optimum point. Okay. The first category is elimination method. Okay, if we know that the function is, the objective function is a unimodal Okay, we can use several methods to eliminate some part out and then iteratively to conduct that algorithm, and then we can narrow down the interval of uncertainty. Okay. So Kadim asked me about how can we make sure that the objective function is unimodal, and I mentioned to you that you must guarantee that you must test against the convex problem, convex function. Yeah, that is true. How about if the function is not unimodal? In that case, you can break the original objective function to be several parts. Okay, you can define the certain region that and guarantee that this region is convex, then it is unimodal. Okay, and the other region you divide, because you divide the original problem into several regions, right? The other region is unimodal, it's convex. Yeah, then you eliminate several parts and then you compare each other, then it is done. Okay, and the other technique is the interpolation. For interpolation, of course, it's involved numerical. You approximate the original problem, the original optimization problem, objective function to be a function in a certain form, for example, a quadratic or cubic. Okay, because of what you know exactly the minimum point of quadratic function. So if you have objective function in any form, of course, it's not quadratic at the beginning, you approximate to be the function to be quadratic, and then you find the minimum point, right? But that minimum point is not real minimum point, because that minimum point is a minimum point of the quadratic function, which is the approximate function, right? From that function, you approximate again using that point to be the quadratic function again, and then you repeat this algorithm. Okay, and the last one is the Newton method. For Newton method, of course, let me share it again. For Newton method, yeah, because the idea, I just derived the formula, the expression we use to calculate the next step. We're starting from lambda I, okay, and then we can find the lambda I plus 1, or the next step, I say the lambda I subtract by f prime lambda I over f double prime lambda I. Okay, this is the heart of the Newton method. Okay. Okay, any questions? I think I will send you the just one moment, the Excel file which I used to construct such the example problem here. Just one moment. I think this, okay. Okay, I send you the Excel file in the line group. Okay, I use this Excel file to generate this example, or this example in the Excel. Okay, so you can understand this example, for example, also this example. It's an elimination method or one dimensional. Yeah. Okay, so wow, I will give you some time to study more on the this algorithm I introduced to you. Okay, so any questions or you have anything to share? So cool, you have any question?
No, Ajahn.
Okay, yeah, take your time to study more on the algorithm I introduced. Okay, so if no more, we finish this class and then see you again next week. Okay.
Goodbye, Ajahn.
Okay, goodbye. Bye bye.